Now, as we discussed the theory of failure, any region that goes below a given line will be a infinite line. Suppose we consider a situation in which we have a Goodman line, which is representing a line between SE and SUT. In this region, if a component will fall having a value of sigma amplitude and sigma mean value, so any value of sigma A and sigma amplitude for this region has a life is greater than 10 to the power 6. That is a infinite life, and the same point will come on this line. Then we have life is equal to n is 10 to the power 6. Or otherwise we can say that if we apply the Goodman criteria, then the factor of safety n will be greater than 1. And on the fence we have factor of safety is equal to 1. And if the point will fall outside, in this case the factor of safety n will be less than 1. Suppose you come across a situation where we have the mean stress and amplitude stress is such that we are getting the factor of safety less than 1. Naturally, the question here is that this will lie outside the boundary in the case of Goodman line, that is a modified Goodman line. So our discussion is we are restricting only the modified Goodman line. And if it will fall, then what is the life of the component? Naturally, this life will be less than 10 to the power 6. So it will be anywhere between 10 to the power 3 to 10 to the power 6. But this time the mean value is not equal to 0. If the mean value is equal to 0, we would have been used the Basquin equation, which one is given as the amplitude stress equal to constant A multiplied by number of cycle to the power B. So this one is a problem in this equation, that if the factor of safety is less than 1, the point will be lying outside the region given by the modified Goodman line, and we are interested to know here what is the life if it will fall outside the region. Consider here that a part is fluctuating between the maximum stress equal to 415, minimum stress equal to 140, and for given part the SUT is equal to 550, SYT is equal to 450. The material strength compared to the 10 to the power 3 cycle, you have to take as 0.9 of SUT. So 0.9 of 550 is 495 megapascal. And let's say we have a endurance strength equal to 275 megapascal. First we calculate here the mean stress, which is nothing but the maximum stress plus minimum stress divided by 2. In this case we have maximum stress is equal to 415 megapascal, which one is tensile in nature. The minimum stress is compressive because it is shown below. So we have 415 plus the sigma minimum is equal to minus 140 divided by 2. So we have mean stress is equal to 137.5 is positive value, is megapascal. So somewhere we have a mean stress here. I will show the mean stress by the dotted line here, and we have value of the mean stress is equal to 137.5 megapascal. So we are handling a situation in which the mean stress is not equal to 0. Then the amplitude stress is given as sigma maximum minus sigma minimum divided by 2. Sigma maximum is same as 415, minus minus become plus, we have 140 divided by 2. So we have amplitude stress in this case is close to 277.5. That will be again a megapascal. So 137.5 plus 277.5, it will attain a value equal to 415. So in this case the stress will change from mean value to max value, and then become again equal to 137, then become the negative value, and finally reach to 140 negative, and in this case the stress cycle is completed. So this value is same as equal to amplitude stress, which come out to be 277.5 megapascal. Now we'll check here the factor of safety for modified Goodman line. Modified Goodman line is obtained by joining the SE with SUT. So we have mean stress divided by ultimate stress plus we have amplitude stress divided by endurance strength is equal to 1 upon factor of safety n. We have mean stress is 137.5, ultimate strength is equal to 550 plus we have amplitude stress is 277.5 and we have endurance strength is equal to 275 is equal to 1 upon n. So in this case we are getting the value of n equal to 0 0.8 which is less than 1. Since we have n is equal to 0 0.8, the part will fail. That is true, but we are interested here how many number of cycles. How many number of cycles the part will attain before its failure. So we have a endurance strength and this one is SUT. So this one is representing the modified Goodman line. Since we have factor of safety is equal to 0 0.8, it will come somewhere here. For the given value of mean stress equal to 137.5 and the amplitude stress is equal to 277.5. If the failure will occur, then we are interested in the number of cycle. So for Goodman line, for the given stress condition, the point P will fall outside and we have factor of safety n is equal to 0 0.8. But for this finding the life here, we normally use the Basquin equation. But in the Basquin equation, which was basically designed for completely reversed loading. So this equation is purely applicable if we have a value of sigma m is equal to 0. But right now we have a value of sigma m and the mean stress here is equal to 137.5. So we cannot use the Basquin equation to find the number of line. So what you do is that we have to replace the value of sigma a by an equivalent completely reverse stress that equal to sigma reverse. But we are also knowing that if any point is lying on the Goodman line, then it has a life equal to 10 to the power 6 cycle. So anywhere on this line we have life is equal to n is equal to 10 to the power 6. Now same concept we'll use here to find the value of the life if we have the mean strength is not equal to 0, that is in this case is 137.5. I will give the procedure here how to go for value of sigma a, that is the completely reverse stress, to find out using the Goodman line. Now one idea is sure about the Goodman line is that all the points on this line has a life equal to 10 to the power 6. So what we'll do in this case, we'll join the point P with SUT and we'll extend this line to find out the new value of the amplitude stress, which one is called as the reverse stress. In any point on this line will have a same life as given by the Basquin equation. But only thing that in the Basquin equation you have to replace the amplitude stress by reverse stress. So the procedure is that join the point P with SUT, extend this line to intersect the y-axis, that each and every point on this line has the same number of cycle. Suppose we have 20,000, then each and every point has a life is equal to 20,000. To find the value of reverse stress, again we'll use the same equation that we have used for the modified Goodman line. So this line has a x-intercept is equal to SUT and y-intercept equal to reverse stress. So we have x upon x-intercept plus y upon y-intercept, that is the equation of line. Using this we can find out the value of reverse stress. So we have x upon x-intercept is same as sigma mean value upon SUT, y upon y-intercept is same as sigma amplitude upon sigma reversible. Sigma mean value we are knowing this time. The numerical that we have taken for example having a maximum stress is 415, minimum is 140, mean stress is equal to 137.5 and amplitude is 277.5. So same example we'll take here. Here we have mean stress equal to 137.5, amplitude stress equal to 277.5. We have SUT is equal to 550, endurance strength is equal to 275 and SYT is equal to 450. Now remember here this method work only for modified Goodman line. So let's substitute for sigma mean is equal to 137.5. We have ultimate strength equal to 550 plus we have amplitude stress equal to 277.5 divided by The equivalent reverse stress is equal to 1. And solve this, you will get the equivalent reversible stress will be equal to 370 megapascal. Now we can use the Basquin equation here. Here S is replaced as sigma reversible is equal to constant A multiplied by life n power is equal to B. And we know how to find out the value of A. So same equation we'll use here. We have A is equal to Sm square divided by endurance strength, and constant B will be equal to minus 1 by 3 into log base is 10 of Sm by Se. Let's substitute for here Sm square. We have material strength equal to 495. So we have 495 square of it, and we have endurance strength is equal to 275. Find the constant A. You will get this constant close to 891. Secondly, find the value of B, which is minus 1 by 3 into a log. We have base is equal to 10. Sm value is same as 495 and endurance strength equal to 275. You will get a negative constant here. So we have value of B is equal to minus 0.08509. And finally, we have to use the Basquin equation, that is sigma reversible, which is equal to 370. We have constant A is equal to 891. Number of cycle you have to calculate. Value of B is minus 0.08509. So in this position, we are able to find out what will be the life, that is a finite life. Now solve this equation, you will get the finite life close to 30585. That will be number of cycle. But my discussion is only for Goodman line. In that case, you have to use the same straight line equation. If it is a Gerber, then you have to use the parabolic equation to find out the reversible stress. The video you are watching is from the app, which is the Mohod class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.